About how the coefficient in front of the a value here would be what we call the amplitude. D would affect the period or the frequency. The D value is just a vertical shift function. Just a minor note I jumped into my head. If you're doing electrical engineering and you have an oscilloscope and you're looking at your signal, your D is what we call the DC, direct current part of a voltage. In other words, your axis is here, you have an AC voltage, but it shows up here on your oscilloscope. You've got a DC component. So this might go between, say, 3 and -3 volts, but it might be up here at 10 above it. It might 13 and 7. But what we're really going to talk about for a little while here is the C value. We looked at this in more general terms for a function, and we know this is a horizontal shift. It's counterintuitive in that when we subtract the value of C, that moves the function over to the right. Which is why I express it as -C instead of +C. C is the value that go over to the right with. So if I have a sine function here, and I subtract some amount. So what am I doing? I'm just moving the whole function over pi over 4 here. When you're doing a horizontal shift on a periodic function, there's something a little special about it, because let's say I were to move this 2 pi, what happens? Maybe I should do this as 2 functions here. So sine of x is 2 pi. Oh. Let's see what happened there. We shift a periodic function over its period back. Right? So it's only shifts that are between 0 and the period that are really meaningful. Like the sine and cosine function, right? Find the sine of 365, that's the same as the sine of 5. It's periodic. So we give this a special name. We call it a phase shift. I guess I've already written that up once. This is a phase shift. Depending upon the terminology you use, you might refer to this phase shift as 360 degrees times C over the period, whatever that is. So what I'm showing you here is a 360 degrees phase shift. Let's put just pi, that would be a 50% or 180 degree phase shift. Or it's going to come up a little later, so I'll say 2 pi 3. So that's a phase shift of 120 degrees. It's a third period. I want to kind of connect this with reality for a minute. Even though this is math, we're not dealing with abstract somewhere. But if you were to hook up your oscilloscope to the power grid here, if you use one of these two plugs here that we use in North America, you would see a sine curve. The amplitude would be 110 volts, 110, 120 volts approximately. The period would be 1/60th of a second. That is, goes up and down 60 times a second, 60 cycles per second, we sometimes say. 60 hertz, same thing. This is a historical thing that we use this particular kind of power. In Europe, jump a little too far here. If you go to Europe, more typically, they have 220 volts at 60 hertz, and they have different looking plugs depending upon where you are, so that you don't plug in your American apparatus and fry it. We do have some Europeans here. Does anyone know the difference between that little guy on the left and, I know these have a ground wire, but does anyone know the difference between these? I'm just curious. I don't know. Oh, I'm sorry. I do know. The one on the right is not European. It's US. It's a US 220. Sometimes you get 220 volt at your home because you have a dryer, right? The dryer will use 220, or possibly a fancy electric range. Okay. But still, again, 60 hertz. Some places in Canada, there's still 50 hertz. This part of Canada, I don't know which. And then we have one more thing, which I think is kind of interesting. It's the whole reason I bring this up. In the U.S., if you're in a factory, you might see a plug like we have over here. You notice instead of 3 wires, a ground and 2 electrical, we have a ground and 3 electrical. And this is called 3-phase. What it is it's like having 3 different 220, 120 volt, 3 120 volt systems hooked up. But as you can see from this diagram, the voltages are out of phase. Why do we do that? Well, as you get this voltage going up, the power you get out of it actually cycles back and forth. It's kind of bumpy. And by putting these things out of phase 120 and 240 degrees, the power you can get out of here is smoother. Typically, they'll take this power and they'll put it through some other circuits that'll smooth it even more. This is an application of the phase shift. So it would be interesting to look at. Any questions on phase shift? Okay. We're going to shift gears a little. We're going to continue looking at graphs, but I want to look at graphs of some other trig functions. We're going to start with the tangent function, which of course is the sine over the cosine. And I want to talk a little bit about this in terms of the unit circle for a minute. All right, the unit circle, points on the unit circle tell us the cosine of theta and the sine of theta. And we're interested in the tangent of theta. So if I start over here at 0 degrees, my sine is 0 and my cosine is 1, so my tangent will be, the sine is 0, so my tangent will be 0. If I swing up here to 45 degrees, the sine and cosine will be the same, so the tangent goes up to 1. And if you think about it, as we move upwards, the sine keeps getting bigger, the cosine keeps getting smaller, so the tangent's going to keep increasing. And then finally, when we get to 90 degrees, what do I have here? My cosine is now 0, my sine is 1, so what happens to my tangent function at that point? It's undefined, right? Tangent is defined. Okay. Now, as I start moving beyond 90 degrees, what happens? Well, my sine is now negative, right? But my cosine is still positive. So I have some big number up here, but it's very negative. So it's very low on the graph. So I get over to 135 degrees, whose reference angle is 45. The two values are again equal but opposite in sign, so it goes down to -1. And then again, finally I get down to 180 degrees, and my sine is back to 0, so my tangent is 0. Okay, that's part 1. I want you to think about that as I do part 2. Here at 180 degrees, as I go further, both the sine and cosine are negative. So that negative sign cancels. So as I move back down here another 45 degrees, this is now 225, my tangent moves up to 1 again. Again, as I move towards 270, the same thing is happening here. the cosine is getting very small and the sine is getting very large, but they're both negative signs, so they cancel out. And then finally I get to 270 where my cosine is again 0, and so the tangent is undefined. And finally, now I move back into the fourth quadrant. The two functions have opposite signs, so my value is now, if my tangent is very negative, starts out very large because the cosine is very small. As I get over here to minus 45 degrees, it's minus 1 again. And then slowly it comes back down to 0. So it kind of looks like whatever goes on between 0 and 180, pretty much the same thing goes on with the tangent between 180 and 360. What does that tell me about the period of the tangent function? The period is pi. It's half. It's half the period of the sine and the cosine. So if I were to write this in a more general form, a tangent of b times x minus c plus d, well, for the sine and cosine, the period was what? It was 2 pi over absolute value of b. The tangent now, period of the tangent, is going to be pi over the absolute value of b. All right, let's take a look at what that looks like. Well, it's kind of strange looking. We'll get to some of the details, but see here we go through the origin at 0. Next place we go through is at pi. And then 2 pi, and look over here at minus pi. So it's repeating every pi. Its period is now pi over b, in this case 1, so pi. Okay, some questions about this. Where is it not defined? I guess I could ask a similar question. What's the domain of the function? In other words, what x values can it have and which values can it not have? We know when cosine of theta equals 0, tangent is undefined, right? So where is cosine of theta equal to 0? Should be an easy question. Alexis is first.
90 degrees?
90 degrees, okay, that's one place. Kira, did you want to? Theta. Really, could be about, what's the cosine of negative 90 degrees? That's 90, so that's negative 90. What's the cosine of negative 90? Get your calculator out real quick.
Zero?
No. I'm sorry, did I say cosine? Yes, it is. I'm thinking tangent. So what's the tangent at minus 90 degrees? Undefined, yeah. Okay, so we know at 90 and at 270, that's the same as 90. Where would I say it's not defined? Theta equal to what? Pi over 2. Then, wait a minute, we've got a function here that's got a degree of pi, undefined at pi over 2. So it's going to have to, that's going to have to repeat, right? It's going to have to be undefined at pi over 2 plus pi n. So that's where it's not defined. Its domain is just, what, everything but that. This should be an even simpler question than these. Where will we get vertical asymptotes for the tangent function? But I draw one in here. No, that wasn't it. Here we go, there's an asymptote. Doesn't that look like one? What happens when we go up here? Just gets closer and closer until we run out of pixels. Same thing over here, going down. See, it's also an asymptote. So where are those asymptotes? Vertical asymptotes. Where do we find vertical asymptotes when you have a rational function? Denominator is 0, where cosine is 0, right? It's the same places, right? Pi over 2 plus pi n. That's where we're going to find these. We've got periodic asymptotes here. All right. So that's the tangent function. Presume you could do the same things with B, C, and D you did with sine and cosine. E will change the period or the frequency. D would kind of move it up or down. C will be the phase shift. The A, which, we usually use A for amplitude. This is not really amplitude. What's the range on this function? What's the range? What's the range? There, nano range, Ohm's range. Mark today's date down as called a sleepy day. Come on, what's the range? What values can the tangent function? Somebody.
All reals.
All reals. Whoever said that, congratulate yourself. Yes, it's all reals. So when I multiply some constant, it doesn't really, you still get all reals. Right? We'll change the shape of this graph a little. I say, put a big number so you can really see. Ooh. Now that's the wrong number. That was the period. Right. Ooh, what happened? Let's try a smaller number. Let's try a very small number. It's just changing the shape of the graph a little. It's just stretching it out or squeezing it in. Okay, I'm going to digress for a minute here. Does anyone know why we call the trigonometric function tangent the tangent function? Do you have any idea? I used to wonder this. I started wondering this about 40 years ago. Nobody had an answer. But then then we had the internet and Google. See, like most of you, I studied geometry and I learned that tangent is a line intersects a circle at one point. And what else do you know about it? Radius to that point and the line have a right angle. Are you familiar with this? Okay, so what does that have to do with this tangent function, the sine over the cosine? Well, it's pretty straightforward. Go back to our unit circle here, and we'll take some angle theta, and let's look at this triangle here. Let's give it some coordinates, A, B, and C. And what can we say about this? Well, we know that AC equals 1 because it's a radius. We know the opposite over the hypotenuse. That's the sine function, right? But that's just BC over CA, or BC over 1. You know, the cosine is what? AB over 1. Okay, that's enough to get started. So now I'm going to draw a tangent. There's a tangent to my point here. And I want to extend AC so it intersects that point. And I'll give these 2 points names too. We'll call this D and we'll call this E. So I hope everybody notices right away that this triangle here, ACB and AED, have something in common. They have some relationship. ABC, triangle ABC, triangle ADE. Anyone see what that relationship is? Theta is the same. Good, good. Also, this angle here, corresponding angle is a right angle. So we know 2 of the angles are the same. We know 2 of the angles are the same. What do we know about the third angle?
Has to be the same. It has to be the same.
Speak up.
It has to be the same.
Has to be the same, thank you. So if all three angles of two triangles are the same, we have a name for that. I'm just curious, I know I'm going deaf. Can anyone in the back, did anyone in the back hear what you said? I am going deaf, all right. They're similar. Yeah, they're similar. And similar triangles have this wonderful property that their corresponding sides are in the same ratio. So let's take a look. We know that, say, BC over AB that's equal to what? ED over AD? Yeah. Okay. But AD, what's the length of AD? It's a unit circle. What's the length of AD? 1. So this length here, ED, is equal to BC over AB. If BC over AB is the sine of theta over the cosine of theta, or tangent of theta. So this length here is the tangent of theta. So I think that's where the name, that's why we named this function the tangent. If you draw this tangent intersecting with this ray, it has that length. Okay. Bugged me for 40 years. Doesn't have to bug you for 40 years now. All right. Go back to graphs for a minute. We're looking at the tangent. What we want to do is look at a related function, cotangent, which is, of course, 1 over the tangent. What do we say about the graph of the cotangent here? Well, there's some things that kind of make sense here. If you look, cotangent has an asymptote at 0. The tangent was 0 at 0. So if we take the reciprocal, you get an asymptote. You're dividing by 0. It also looks like the tangent function is kind of the cotangent function is the tangent function sort of upside down. In other words, cotangent, like negative tangent, we should have an x here. But not exactly, right? I mean, if I turn the tangent function upside down, what happens? Oh, okay. So now what's the difference between these two?
They're out of phase.
Whoever said that? I'm so happy. They're out of phase. Yes. We need to adjust them. How do we adjust them? I heard something. Add? Well, actually, we can go either way, can't we? All right? We can go over to the right. Let's see, how far do we have to go over to the right? Pi over 2. All right, let's try that. So these two are pi over 2 out of phase. Now once you put the negative sign on. The phase shift, since the period of the tangent and the cotangent is just pi, phase shift of pi over 2 is 180-degree phase shift. All right. That's probably most of what you need to know about the cotangent. You know the tangent, you probably know the cotangent. So let's move on to the reciprocals of the sine and cosine. So 1 over the sine function will be what? What's that function? Cosecant function. Well, cosecant function is going to have a lot to do with the sine function. But the sine function occasionally is 0, right? So we're going to see some asymptotes, right? Where are we going to see them? Wherever the sine is 0. So if you look on here, where else is the sine 0? It's at 180 degrees, right? It's pi. Whenever you're graphing the cosecant or the secant, I always think it's a good idea to graph their reciprocal first, and I think you'll see why when I put this graph on here. Okay, so you can see right away there's an obvious reciprocal relationship here, where the sine function is 1 at pi over 2, the cosecant is 1 also. They intersect. But from there on, the cosecant is the reciprocal, right? As the sine gets close to 0, the cosecant follows that asymptote up to infinity. Similarly here, in the third and fourth quadrant, the two meet at -1. And then the cosecant is going to go down to minus infinity on both sides. Okay, let me just ask a few questions. So, where, I think I answered this already, where is this function, where's the cosecant not defined? Oh, it's not defined where sine of theta equals 0, right? So where is that? I guess we decided that was it. No, I guess we didn't. Here is the sine of 0, 0. Sine of theta 0. Theta equal what?
0.
0. Good. Anywhere else?
5.
5. 2 pi. Yeah, it's just pi n. Okay. Every pi in both directions. That's where the asymptotes are. The complement of that is its domain. Right? That's where it is defined. Right? So everywhere but those. What's its period? And how far do I have to go for the cosecant repeats. Go over here, that's pi. Over here to 2 pi. And we see it repeats again. So the period is just this plain old cosecant is 2 pi. But if you had cosecant of b times theta, right, it would just be 2 pi over b. If I feel like I missed something when I was talking about the tangent would be what? Tangent b theta, what would the period be? Because a tangent has a period of pi normally, so if there's a, this is in the way, there's a b, what's the period of the tangent? It's just going to be pi over absolute value of b. Right. Last question about cosecant. What's its range? What values can the cosecant have? Not being very brave today, are we?
Is it a -1 and 1?
What about -1 and 1?
Is that what it
Has to do with -1 and 1.
is? The range.
Range is just -1 and 1? It can be -1 and 1 because the sine of pi over 2 is 1. So 1 over 1 is 1, and the sine of 3 pi over 2 is -1, so it can be -1. Yeah.
So like it would be x is greater than 1 and x
Greater
is,
than or equal to?
yeah, greater than or equal to, sorry, and less than or equal to -1.
Okay, so, or we could say absolute value of x is greater than or equal to 1. How about that? Yeah, it's everything, except for 1 and -1, it's everything that the sine function isn't. It's everything outside of it. Okay. I guess I should mention, of course, since we have the cosecant function, we also have the secant function. Oops, I didn't want to do that. We also have the secant function. What's that going to look like? Well, it's just the cosecant function shifted. Right? If I were to graph the cosine of x, right, that's the function that you associate with the secant, it's the reciprocal, and it has that same relationship. It intersects at 1 and -1, and everywhere else it's the reciprocal. Good on graphs of trig functions?
Professor, I just wanted to say, shouldn't it be y instead of x? Because we're talking about the range, right?
Yes, thank you. Good job. I mean, if you said this, if you said, you know, the range is equal to x such that absolute value of x is greater than or equal to 1, that would still be true because x is just a dummy variable here. I'm just saying, you know, x and the reals, blah, blah, blah. But you're right, I'm just going to throw something out like this. I should be accurate. Okay. A little bit more about trig functions. There's a special property. I can put this away. No, I don't want to put it away. Just close it up for now. There's a special property of the tangent function that's nice to know. We're going to go through memory lane here. We're going to go back to algebra 1. And we're just going to look at a very simple function, y equals 2x. Well, let me graph that. 2x plus b, where b is 0, so you know it's going to go through the origin. And I know the slope is 2 over 1, that's my delta y over delta x, right? So I just have to pick a point, 1, 2. Okay, there's my y equals 2x. But if I pick any point on this line, I'll just pick 1, 2, it's easy. And I draw an altitude down. I have a nice triangle here, and I have an angle theta, in the position I like to see it in. And I say to myself, got an opposite and an adjacent here. What's the opposite over the adjacent? That's my tangent of theta, right? And coincidentally, that's 2. Clearly, that's opposite over the adjacent is the same thing as delta y over delta x. That is, for my equation, y equals mx plus b, m is the tangent of that angle that the line makes with the axis. So if I gave you a problem, I said, well, I have a line that goes through some weird point. It goes through, say, 5.6, right? And it has an angle of 32 degrees. And I said, what's the equation of that line? Whereas before we would kind of scratch our heads and go, I don't know. We could figure it out with some trig functions, but we can go right to it here. It's just y equals m, which is the tangent of 32 degrees, x plus whatever my intercept is. So, more to say about it. It's just lucky coincidence. Tangent function corresponds with something we're familiar with. Okay, I think it's almost all we're going to do with graphs of trig functions. I have something else I want to mention because I think it's kind of neat. It's not be part of the curriculum, but it has to do with trigonometry. And I might have to search around for a minute to get okay, a little trip through memory lane here. Oh no, it's not here. I have to search around. Let's just go to Google. That's a good place. Ah, that looks pretty. Okay. Everyone familiar with this? Well, this is actually, it looks like an image. An image. But we'll call it a map here. Is everyone familiar with this map? This map, which is, as it says, is a Mercator projection. It's famous for something really odd. It's famous for students, growing up in their grammar school classes or their high school classes, having a really distorted view of the size of the world. Specifically, if you look up here we have Greenland. You know Greenland, in this picture it's white, but it's turning green again because of global warming. But you compare that with South America, and you think, Greenland's at least the size of South America. It's probably the size of Africa. It's not, right? Greenland is much, much smaller. Similarly, take a look at Alaska here. Alaska is about the size of half the U.S., looks like at least. So these are all incorrect. I read somewhere something interesting. They said because of the Mercator projection, oops, how did that happen? Go back. That Russia looks much bigger than it actually is, and it scares people. It's so big. I don't know if that's true or not. So the question is, why is this really distorted map ubiquitous? We find it everywhere. And, that's one question. Another question is everybody familiar with this? Anyone not seen this before? Some in my last class have never seen this. Interesting question is, where is the North Pole? Where is the North Pole? It seems like it's just off the edge of the map, doesn't it? Yeah. Actually, the way this Mercator projection is done, it's up at infinity. That's how far away the North Pole is. You have to go to infinity to find it. Same thing with the South Pole, except in the other direction. So what is it? Why is this everywhere? Well, there's kind of a mistake involved. This used to be an extremely common map in, I don't know, probably the 15, 16, 1700s. People were sailing the Atlantic. Columbus came over and bumped into North America. And it turns out that this map is really useful for sailing, if you know what you're doing. For most maps that aren't distorted this way, if you're at point A and you want to go to point B, if you're the navigator, if you look at the map and you draw a line, this is not the most direct route from A to B. Instead, the most direct route will look like this. It'll be what we call a great circle. But the Mercator projection has this wonderful feature that if you draw a straight line on the map, it's a great circle. It's a straight line on the globe. So if you're a navigator and you want to know which direction to go, this will tell you. You have to realize that the distances aren't right. But, you know, you're in a sailboat. What are you going to do? Speed up the boat? Speed up the wind? Okay, so why all this? Why am I showing you this Mercator projection, pointing out this distortion? Well, if you had a map where you put the latitudes, right? 0, say, 10 degrees, minus 10 degrees, 20, 30, 40, 50, I guess you'd go up to 90. How do you construct this Mercator projection? Well, what you do is you translate each of these latitude lines to a new location, specifically to the tangent. Now you know why the North Pole and the South Pole are off at infinity, right? Because the tangent of 90 degrees is what? Well, this is minus 90. The tangent of minus 90, that's minus infinity. That's 1 over 0. So anyway, I just thought this is just an interesting feature of the tangent function. This is how we create this Mercator projection. Okay, I think that's all I have for you today. I'll be in my office in a few minutes.